day, folks. Welcome to my YouTube channel. If you're new here, don't forget to subscribe and watch my videos till the end, and like and subscribe and share with your friends. Today I'm going to look at the vertical projectile of motion with the hot air balloon, specifically the two balls, which is one of the complex questions, but I'm going to try to make it as simple as possible. A hot air balloon moving downwards at a constant speed of 3 meters per second, right? So this hot air balloon is going down at a constant speed. We know if it moves at constant speed, that means the acceleration is 0. And then we're going to choose down as what? As positive, and our gravitational acceleration will be positive, 9.8 meters per second square, right? But the hot air balloon is not accelerating, but generally our 9.8 for the balls, because the balls are not moving at constant velocity, right? Now, when the hot air balloon is 10 meter above a tall building, so here's the tall building. So above the tall building, it's 10 meter above, right? A ball Y is dropped, very important. So when something is dropped, its initial velocity is 0. It's dropped out of the hot air balloon. And another thing, guys, the object, which is the ball, the initial velocity of ball Y is equal to the velocity of the hot air balloon. It's very important, which is the velocity of the hot air balloon is what? Is 3 meters per second. So now the object was moving with the velocity of the hot air balloon, and then it was dropped. So if it's dropped there, its initial velocity is not going to be 0. It's going to be the velocity of the hot air balloon. That's 3. Very important. Now it says 1 second later, another identical ball X is dropped from the top of 60-meter tall building shown in the diagram below. So ball X is dropped there. So ball X, its initial velocity is equal to 0, right? So it's going down, right? So now, shown in the diagram, ignore the effect of friction. So guys, what's going to happen as the hot air balloon is descending, when it was 10 meter above the tall building, the ball X was dropped. So the ball X, its motion is going to go down with its initial velocity, which is what? 3, right? It's very important, right? Okay, let's go and answer the question, and then I'll explain the other stuff when we answer the question. In 3.1, it says write down the initial velocity of ball A of ball Y. As I've mentioned, it's going to be 3 meter per second. Its initial velocity is going to be 3 meter per second, and it's very important to write even the direction. It's downwards. It's 3 meter per second downwards. It's 2 marks there. It's going to be a mark for this, a mark for that, I guess, right? After ball Y is dropped, it is ball Y in a free fall, right? Only yes or no. So it was not on a free fall while it was here at the ball Y, but as soon it was dropped, it became in a free fall, because while it was on a hot air balloon, the force that was acting there, it was not only gravitational force, there was the force of the fire, which is the force that propels the hot air balloon. So there were more there was another force that was acting there except the gravitational force. So now as soon as it was dropped, it became on a free fall. So the answer here is yes, right? So it says give a reason for your answer. You will say there is only one force acting on it, which is gravitational force, right? Okay, now guys, calculate the speed with which the ball strikes the ground. So which ball X. So for ball X, it starts from there, and its displacement is going to be 60 meters, and it's 60 meters downwards, which is positive, and its gravitational acceleration. Okay, let's calculate it here. So 3.3, we want the final velocity, right? The initial velocity we have, it was what? 0, because it's dropped. Do we know the time? No. The acceleration we do have, it's positive 9.8. Remember, we chose downwards as positive. And then the displacement is going to be positive 60 because it's traveling from there to there, 60 downwards. So which formula are we going to use? We're going to use this formula that says Vf squared, V initial squared plus 2 change in y. And then we substitute. The final velocity is the one that we want, and the initial is 0 plus 2 times 9.8, and the displacement is positive 60. And then if you put that in the square root, and punch that in the calculator, your answer will be square root 2 times 9.8 times 60. It's 34.29 meter per second, and it's going where? Downwards. It's downwards, right? Let's now we know the velocity that it's going to reach the ground, the ball x. Now 3.4, it says determine the time when the ball y passes ball x. This is a complex question, guys. It's very important. It's a complex question. So what are we going to do? Let's assume that ball x and y, they meet here. Let's say they met here. This is ball x and this is ball y. Now here, if you look at ball x, it traveled this distance from here to here. So the distance it traveled, it's that dy, right? But look at ball x. The ball y, they travel the same distance while it was here. The ball y will travel from there to there as soon as it passes the edge of the building. From there to there, it's the same distance. So meaning that ball y travel the same distance with ball x, but with an extra 10 meter. So now what I can say now, the displacement of ball x y, it's going to be same displacement, which is from there to there plus the 10 meter. So the displacement of I can say the displacement of ball y is going to be dy plus 10. That's the displacement, which is, it's this displacement plus the 10, right? So when they meet at this point now, what are we going to do? We're going to equate, they meet at the same point. We're going to equate this displacement that ball x traveled with this displacement. And another thing that is important here, we were told that 1 second later another identical ball is dropped from the top of the building. So it means this: the time of ball y, the time of ball x is equal to the time of ball y minus 1, because ball x was dropped 1 second later from the time of ball y. So the time that ball y traveled, it's 1 second later. So the time for ball x is equal to time for ball y minus 1, because it was thrown, ball x was thrown 1 second later. That's what you do always. When it's 1 second later, you say minus from the first ball that it was thrown, right, at the time. Okay, so 3.4, what is the ax here? It says determine the time when the ball passes each other. So we wanted the time when they pass each other here. So what I'm going to do, I'm going to solve this simultaneously. I'm going to create equation for each ball, right? I'm going to create equation for each ball. So I'm going to do for ball y, right? I'm going to create an equation for ball y. So this, I'm going to use the formula that says dy is equal to, okay, let me write things that I have for ball y. What are the quantities for ball y? The quantities that I have for ball y, it's, I have what? Well, what do I have? It's the displacement, yeah. The displacement for ball y is equal to dy plus 10, which is plus 10 meter, as I've mentioned here. The distance that was traveled, it's this displacement, which is dy, which is same distance as x, but it has an extra 10 minutes there, right? And it's going in the positive direction. And then whatever time, we do not have time for ball y. We do not have. And what else we have? We have an initial velocity for ball y. The initial velocity is positive 3 meters per second because it's going down, right? And then we do not know the final velocity when they meet for ball y here. We do not know this velocity when they meet here. The initial is 3 there, and then when it gets there, we do not know the velocity, so leave it like that. Even we want the time. Guys, this type of question, you use a simultaneous equation, right? So using simultaneous equation, you have to create equation to equation. So I'm going to create an equation for y. So the equation, I'm going to use the formula that says delta x y is equal to v change in t plus half a t squared, right? So what is the displacement for y? Okay, the reason using this formula is because I have the displacement for y, and the initial velocity I have, it's 3, and the time I have, the time is just, I do not have, I'll just put t, and then that's what I'm looking for, it's t. So using that equation, let me substitute. So it's going to be delta y plus 10 is equal to the initial velocity, it's 3, and then the time we do not have, it's change in t, plus half acceleration, it's positive 9.8, and the time is change in t squared, right? So here I'm going to create the equation 1 for y. So this is what I have. I will have so this is going to, I'm going to leave the y here since I'm going to use the simultaneous equation. So I'll have 4.9 change in t squared, which is this, and then plus 3 change in t, and then minus this 10. I'm going to transpose it to this side. It's going to be minus 10. This will be my equation 1. I hope that makes sense. And then now let's go to ball x. I'm going to create an equation for ball x. The displacement for ball x is equal to change in y, right? It's for ball x is equal to change in y, and the time for ball x, remember, the time for ball x is equal to the time for ball y minus 1, as I've mentioned earlier. That's the time, right? And then its initial velocity, the initial velocity for ball x is equal to 0 because it was dropped from the 6 meter height, and then the final velocity when they meet is unknown there. So we're going to use the same equation that says delta y is equal to v initial change in t plus half a t squared. The reason we choose this formula again is because it doesn't have the final velocity, because we do not have the final velocity for both balls when they meet. So the displacement for ball x is change in y equal to the initial velocity. It's what? It's 0. It's 0 times change in t plus the acceleration is positive 9.8. Guys, they can never have different accelerations, different directions of acceleration. And then the time Okay guys, I was supposed to, but since it's going to be 0, I was supposed to here, it's going to be delta y 0, and then the time, it's going to be this, it's going to be change in t minus 1 plus, and then here it's change in t minus 1 square, because there's a square there, remember. And then delta y is equal to this, so this is 4,9, so it's going to be 4,9, right, which is, this is going to be change in t square minus 2 change in t plus 1. Guys, I'm sure you know maths better than me. So, and then we distribute that. Is going to be 4,9 change in t square minus 9.8 when we multiply this by this. So 9.8 change in t, and then 4.5 times 1, 4.9 times 1 is going to be positive 4.9. So that will be equation 2. So if you're looking at our equation, what is common between, we have y, change in y, and change in y. So we're going to equate the two. We'll say change in y is equal to change in y. The other is for x and the other is for y. Okay, so I'm going to take this one. It's 4.9 change in t square plus 3 change in t minus 10 equal to this one. It's 4.9 change in t square minus 4.9, no, minus 9.8 change in t plus 4.9, right? Guys, if you can see here, if I take this to this side, it's positive and it's positive. So if I take it, it will be negative and they will cancel each other. So we just cancel them. And then I group the like terms. So it's going to be 3 change in t, and then I take this to this side. So it will be plus 9.8 change in t equal to, and then I take the 10 to 4.9. I have 4.9 there, and I take the 10. The 10 is positive, and it's going to become, it's negative, it's going to become positive. So here in this side, we're going to, these are the like terms. So it's going to be 12.8 change in t equal to 14.9, and then we divide by 12.8 both sides. 12.8 both sides. So it's going to be the time when they meet. Now this is the time. It's 1,16. 1,164, or you can just say 1,16. 1,16 seconds. So when they meet here, at this point, they meet at after the question was says determine the time when they meet at 1.16 seconds, right? Let's go to the last question. The last question, it says on the same set of axes, sketch the position time graph for the entire motion for both x and y for from the time they drop until the ball strikes the ground. Use the ground as a reference. Indicate the following. Okay, so the position versus time graph, it's gonna be like that. And this is time in seconds, and then this is going to be position in what, in meters, right? So let me start with the easy one. Let me start with the x. The x was thrown from the 60-meter height, right? And then this one was dropped. This was dropped from a 60-meter height. This one was dropped 60 plus 10 from 70-meter height. So our heights here, it's going to be 60, and then we're going to have what, 70, right? So basically, when something is dropped, the position versus time graph for 60, it's going to take a curve like that, curves like that, but that's where they meet. So we need to be careful when it comes to that. Let's start with the ball x. Let's start with the ball y. The ball y, it was dropped. I'm gonna use different colors. This is ball y. ball y was dropped and reached the ground there, right? And then ball y, guys, is going to reach the ground before ball x, because this was thrown. Ball y is going to reach ground before ball x because this was thrown, so it will be faster, because this is thrown 1 second later and it's below. So even if it's below, but it doesn't reach the ground first, because the catch-upping here, which is the mid here, it shows this one is faster. So that's the curve. This is the curve for y. Okay, let me label it and say it's y. This is the curve for y. And then the curve for x. Guys, I cannot start here. I cannot start here for x, right? Because ball x was thrown 1 second later. So if I start here and do the curve like that, it means they started at the same time at t0. No, ball x started at 1 second later. Let me use a red one. 1 second later. We'll just say 1 second is there, right? So we'll just do this. It started 1 second later. So the curve, it's going to be and remember, ball x, it reached the ground later, so which means this time it has to be longer than this time that ball y got in the ground. So it's going to be something like that. I'm not good in drawing, so it's going to be something like that, right? That's not a nice curve. Yep, it's going to be something like that. So this is ball x and this is ball y, right? So guys, this is where they met, the time they met, which is the one that we just calculated. It's 1,16, right? That's 1,16, and then this is the height where they met, which we do not know the height where they met, and ball x was thrown 1 second later, so we should take that curve. Okay, whatever. So guys, that's the graph. That's the graph. I didn't even read what they wanted. The initial position of ball x. Here's the initial position for ball x, and then the time for ball y passes. Okay, this is the time. Shown that, guys. I hope this makes sense. Hope this makes perfect sense. Cheers, bye.